electrophilic substitution is taking place on the aromatic compound. It is called electrophilic aromatic substitution. Let us see the mechanism. This is benzene ring with a hydrogen. I can point out any hydrogen, just for convenience I showed this hydrogen. Now this electrophile attacks on this carbon atom. Once it is attacking on this carbon atom, this bond automatically shifts here. That is, this electron is moving towards the electrophile. So this carbon atom lost this electron. That is why positive charge on this carbon atom that is given to this electrophile. So electrophile which is having a positive charge got this electron. So that is this electron. So no more positive charge on the electrophile. Now this is the first carbocation that is formed. This carbocation undergoes resonance to make it more stabilized. So this double bond shifts here. As a result, this electron is lost and it is coming over here. Since it is coming over here, no need of positive charge here, but electron is lost from here, so positive charge here. Repeat the same thing. Again, this bond shifts here. That means this electron comes over here. So this positive charge is nullified, but this carbon lost the electron, so positive charge over here. That's what we are writing here. So these three are shown by reversible arrows. That means they are resonating structures. All the resonating structures are represented by a resonating hybrid, which starts from positive charge from here and ends at positive charge here. That is why positive charge from here till here. This is called erinium ion complex or sigma complex. This is the reactive intermediate. Here the positive charge is not sticking to one position, it is not localized, but it is moving to all the positions. So we are calling it as delocalized. Delocalization of charges gives extra stability. Now comes to the final step. Take any of this. Let us take this one here. This bond shifts here. That is, this electron shifts to this position. So this positive charge is nullified. A bond is formed here. The hydrogen lost its own electron, so it is coming out as H+. So if you look at the overall reaction, the overall EAS reactions are exothermic. That is, they release energy outside. Look at the overall reaction. There are two major steps involved. First step is attachment of electrophile by breaking the double bond. Second step is breaking the CH bond. First step is reversible, that is, it is a slow step, and this is called as the RDS. RDS means rate determining step. That is the slowest step. Overall speed of the reaction is decided by this step. So if you draw the energy profile diagram, this is the activation energy required for the first step, then forms the reactive intermediate, which is the erinium ion complex. Then the activation energy required for the second step, where it forms the products. This is the reactant, this is the product. So as you can see, activation energy required for the second step is low. That is why it proceeds quickly. But activation energy for the first step is high, so it takes more time. That is the slowest step. But keep a note, this is different for sulfonation and iodination. For all reactions, this is the profile. But sulfonation and iodination, the graph somewhat looks like this. Both are equal. So this is not the RDS, but the second step becomes the RDS for sulfonation and iodination. So this is the overall EAS reaction. All electrophilic aromatic substitution like nitration, sulfonation, Friedel-Crafts alkylation, acylation proceed by the same mechanism. Only the electrophile is different in all the cases. How the electrophile is generated? It is depending on the type of the reaction.